This test stand is set up to demonstrate the effects of pulsation from a reciprocating pump with a high discharge and with a high inlet pressure coming into the pump. This simulates a tall tank feeding the inlet into the pump, and we've accomplished this by using a forklift and a tub of water approximately 16 feet in the air. The test stand consists of a 2-inch air-operated double diaphragm pump, a Blaco discharge pulsation dampener with the adjustable control, a Blaco inlet stabilizer with the J model or inlet control, and we're using a transducer to show the effects of the pressure spikes created as the inlet valve balls to the pump alternately open and close. This creates a water hammer which can create a pressure spike that can damage the diaphragms in the pump, greatly reducing their life. The J model inlet stabilizer has been overcharged, so its bladder has been pushed down into the inlet and the stabilizer shut off. So in effect, it might as well not be in the system. The discharge dampener has already been recharged to the proper pressure charge. You can see that the discharge pipe is dampened, non-vibrating, and the discharge flow is continuous and non-pulsing. The discharge pressure gauge reads steady. The inlet side of the pump is shaking violently, and you'll notice on the transducer that with every pump stroke, the pressure spikes are reaching as high as 20 psi. Now, most air-operated diaphragm pumps tell you in their instructions not to exceed 15 psi inlet pressure with rubber diaphragms or 10 psi with Teflon diaphragms. So you can see that we can be doing damage to the diaphragms with this kind of pressure spike. As we tune in the inlet stabilizer, we can see in this transparent inlet stabilizer that the pump pulse or water hammer is now being absorbed inside the inlet stabilizer instead of slamming into the pump. What occurs is that as this acceleration head from the high tank flows down and the inlet valve balls close in the pump, they momentarily stop the flow and a pressure spike is created. The pressure spike can't go back up the discharge line because of the positive head. However, the other side of the pump is opening its inlet valve ball to accept liquid. It's now a low pressure area. The spike rushes over there, slams into the diaphragm, and distorts it. With a rubber diaphragm, it stretches and tends to separate the rubber from the fabric, causing it to leak, tear, and fail. If it's a Teflon diaphragm, it starts to cold flow under this unbalanced pressure, stretches, and fails. Now that the inlet stabilizer has been adjusted by lowering the pressure charge within it, if you notice on the transducer, the pressure spike has been absorbed by the inlet stabilizer and the inlet pressure has now been reduced significantly. That amount of pressure spike is well within the limit of the air diaphragm pump and no damage will occur to its diaphragms. The valve balls will seat more positively and there is less chance of cavitation because we are accumulating liquid right at the pump's inlet. Also observe that the inlet pipe is now nearly vibration free and protected from damage to joints, threads, gaskets, gauges, and other components on the inlet side of the pump. We have, in effect, turned a reciprocating positive displacement pump into a centrifugal pump from a flow and pressure point of view. If the pump's inlet was working with a suction lift or vacuum condition, the inlet stabilizer would be adjusted to have a vacuum of 4 to 6 inches of mercury in it. This is accomplished by blowing compressed air through the J model's control valve with the ball valve open. We hope that this demonstration has shown that with the use of a discharge dampener on the discharge pump and the inlet stabilizer on the inlet side, we can protect the pump, the piping, and system components. We know that adding a pulsation dampener and an inlet stabilizer will extend the life of your liquid handling systems components and, most importantly, protect your system, allowing you to pump and transfer more products for a longer period of time between maintenance and repairs.